Greetings, aspiring scientists. Welcome to my video today on homologous series in organic chemistry for the IB curriculum, chemistry. So my previous video was very long, but it already talked a little bit about homologous series, so I'm just going to expand on that today. Let's go to my slides. So this is 3.2.3 in structure. We're almost done all of the structure content. I think just this video and one after. So the word homologous you might know from other things, like if you studied biology, there's homologous structures and analogous structures, but homologous generally just means same structure or same history, same line, and its meaning is very similar in chemistry as well. So homologous series. Homologous series are a series of similar compounds that only differ in carbon chain length. Usually, which is the number of CH2 groups on the structure. So when it's very small, it's not going to be a CH2 group. For example, going from methane, CH4, to ethane, CH3, CH3, connected together. That does not differ by a CH2 group, but it does differ by one carbon, at least in the structure. But once they start getting larger and larger, they're only going to be differing from their previous and forward neighbors by a CH2 group each time. So mathematically, this forms series of CnH2n plus X for hydrocarbons. So we're taking hydrocarbons to be alkanes, alkenes, alkynes, and cycloalkanes, or alkenes, that can have cyclical structures, ring structures. Now, if there's only single bonds in your hydrocarbon, your series is CnH2n plus 2 alkanes. But if you have a double bond or a ring, a cyclic structure in your compound, your series is CnH2n. Alkenes or single rings. If there is one triple bond, your series is CnH2n minus 2. It's kind of a general formula that can describe that triple bonded structure in the hydrocarbon, but it may not be a triple bond. It could be two double bonds in different locations. It could be one ring and one double bond. Various combinations of what we call unsaturation are possible, where some hydrogens that could be attached there have been removed and there are multiple bonds or rings instead. So again, that's summarized here. Hydrocarbons are generally CnH2n plus some number X. For alkanes, X is 2. No double bonds or rings. For alkenes, X is 0, CnH2n. You have exactly double the amount of hydrogens to carbons. So that's alkenes, one double bond, assuming no rings. And then CnH2n minus 2. Alkyne, one triple bond, which is assuming no rings or double bonds. As I mentioned, various combinations can lead to this formula on the left, but definitely alkynes does fit in here as the main one. So I have to talk about the word saturation again. I've been using it a little bit, especially in my previous video, but organic molecules can either be saturated. That's a word that you might know with regards to solutions. Like a saturated solution has sort of the maximum capacity of solute in it. But a saturated hydrocarbon or organic molecule contains the maximum amount of hydrogens bonded to carbons. So molecules can either be saturated or contain some amount of unsaturation. They can contain areas where hydrogens, you can imagine, have been removed and there's now multiple bonds or ring structures. Unsaturated molecules have double bonds, triple bonds, or cyclic ring structures where hydrogens or other bonds could be added. Too many others there, to make new saturated chains. Now, I think some definitions call rings possibly already saturated, but I like to think of them as being a little bit unsaturated because you could open up the ring and add hydrogens wherever you make that cut through the ring. but it kind of depends. I'm not exactly sure what IB would prefer. Generally, I don't think they'd give you that kind of question, like, is this ring saturated or not? But you probably should say that it is saturated if it's just a aliphatic alkane ring. Anyway, unsaturated molecules tend to do a wider variety of chemical reactions for this reason. They have areas where addition can happen, or polymerization, or ring opening reactions. So here's just a little infographic type thing I made with Claude. So saturated, an example is butane, 4 carbons in a row, hydrogens attached to every other spot. Key properties, these are all CC, single bonds, wherever there's a carbon-carbon bond. It has the maximum number of H atoms, as long as all these carbons are still connected together. Every other position has a hydrogen. That's saturated. Generally solid at room temperature. You can think of fats like butter, lard, wax.
Okay, so I've written here that saturated fats are often solid at room temperature, things like butter. That is true. That's mainly for things like fatty acids and triglycerides, especially special types of macromolecules, biomolecules. But just the regular alkanes like ethane, propane, butane, and all the way up to 10 or 15 carbon chains even, there's still going to be liquids or even gases for the very light ones. They're just not large enough to be solids. And similarly, on the other side, I say unsaturated fats are often liquid. Again, that is true for the biomolecules, lipids, but for a lot of the very light ones like butene, propene, they're going to be gases just because they are so light.
They're generally less reactive. As I said, they need activation from like a radical halogen reaction or something. They have the general formula CnH2n plus 2, so real saturated alkanes, aliphatic molecules. On the other hand, then, unsaturated, an example is 2-butene, C4H8. That's the CnH2n. It has exactly double the hydrogens. But you can see this double bond now, CC double bond in the middle of this molecule. Key properties: contains some CC double bonds, or possibly triple. It has fewer H atoms than the saturated version, generally liquid at room temperature, oily oil type things, for example, olive oil, fish oil, many vegetable oils as well. But if you remember in my previous video, I talked about hydrogenation and how sometimes we can mess up natural unsaturated fats to go from being the cis configuration to the trans configuration. So cis was when the chains on this are on the same side, like how it's drawn here in my diagram. But when your chain continues downward in both directions, like I've drawn it here, that's cis, that's naturally occurring kind of unsaturated fats. But the trans version, which is normally only made in the laboratory, man-made kind of creation, can happen when the chain continues on opposite sides of this double bond. And that actually gives it more properties to saturated fats, saturated oils, saturated kind of hydrocarbons, because it's able to stack very similarly to saturated molecules. Saturated molecules generally can get very close to each other, stack up like this, have a lot of strong London forces, intermolecular forces. And so can unsaturated trans versions of these hydrocarbons. But the cis ones, as I mentioned, it's hard to imagine, but if you have these kind of like multiple cis structures, even just one is probably enough to make them not be able to stack nearly as well as saturated or trans unsaturated oils and fats. That keeps them liquid and fluid and not blocking anything in veins and arteries. Alright, it's a bit of a tangent, but I think it is important to know. So, chain names, main chain names. This is where we start getting into naming. My next video will be really about naming, but this is the first step in learning how to name these compounds properly. IUPAC root names. I forget what the acronym IUPAC stands for. I think it might be French, somewhere in Europe, but it's the official governing body that rules names and definitions in a lot of science and chemistry. So for organic carbon chains, we have root names that you absolutely must know. You must memorize these as soon as possible. You know, just go through this 50 times if you need to. 1 meth, 2 eth, 3 prop, 4 bute, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, 10 dec. And oftentimes we'll add an AN as well on this root name to extend it into certain names. So methan, ethan, propan, butan, pentan, hexan, heptan, octan, nonan, decan. Okay, so just say this like 50 or 100 times, however long it takes you to memorize it. Do practice questions with it until you can get it. Flashcards, whatever you need. So we can look at the homologous series of alkanes, CnH2n plus 2, methane, ethane, propane, butane, pentane, hexane. So you can see the alkane naming system has a suffix, an ending of ane, just like in the word alkane, its class. That becomes the suffix in the name of all these. That will generally be the case. So methane CH4, ethane C2H6. So you can see the difference between methane and ethane is not exactly a CH2 group, but going from ethane to propane to butane to pentane to hexane, that difference is always one of these CH2 groups. We're just adding in between on the chain. That's the way homologous series generally work, especially from the second or third one in the group. And then you can see the full structural formula underneath. We're just adding CH2 to the chain, making it 1 carbon longer. Good. Next, functional group series. So all the functional groups that I had in my previous video and that are in the IB syllabus and textbooks, they have their own homologous series as well, because you can just keep extending the chains on them, the carbon chains, by adding CH2 groups. So we had alcohols, CnH2n plus 1. This is generally the formula COH attached to some other chain. So I have 3 R groups there, where R can be carbons or hydrogens. Whether or not it's carbons or hydrogens will determine whether this alcohol is primary at the end of a chain, secondary in the middle, or tertiary in the middle of a branching section. Then we have ketones, CnH2nO. This is generally C double bond O with some R groups attached to that carbon. R for ketones is always carbons though, because you can see underneath, if it's hydrogen, that makes this an aldehyde instead, but it has the same general homologous series formula, CnH2nO. So you got to start to be aware of these, which ones might have the same homologous series. So here's a couple others. Alkenes, CnH2n. Alkynes, CnH2n minus 2. Halogenoalkanes, CnH2n plus 1x. So for alkenes, we go ethene, propene, bute, 2-ene, pent, 2-ene. don't worry too much about these numbers. I'll talk about that in my naming video next time. But you can see how it kind of goes. The alkenes have the suffix ene, ene. Ethene, propene, butene, pentene. And again, the root names are just how long the chain is. Eth, prop, but, pent. Alkynes then, that suffix becomes -ine. Ethine, propine, but to -ine, pent to -ine. They have a triple bond somewhere. And then as we go down the series, we're just adding more carbons on the chain, making it longer. I apologize for some letters being larger. It's just I made this with AI and it made so many mistakes. I had to fix them myself. Hopefully I did fix them all. Anyway, halogenoalkanes, CnH2n plus 1x, chloroethane, chloropropane, chlorobutane, chloropentane. So we get the halogeno being whatever the halogen is. In this case, I chose all chloro. This becomes a prefix instead, something you'll have to get used to and memorize. Doesn't become a suffix. The suffix just remains the alkane name, ane, A-N-E. And then the root tells you how long this chain is. Alright, not too bad. Some more alcohols, CnH2n-1OH, ethanol, propanol, butanol, pentanol. So again, part of the name from the class, that ending becomes the suffix on all of these. All, in this case. All. Aldehydes, CnH2nO. This suffix is rather unique. It doesn't really match the ending of the name, but rather the beginning here. Al, ethanal, propanal, butanal, pentanal. And again, going down the series, it's just increasing the carbon chain length by 1 each time. But you still have the same groups on the end. That's what makes them in the same homologous series. Now, ketones. We can't have a C2 ketone. A ketone is a carbonyl group, C double bond O, in the middle of a chain. But if we only have 2 carbons, each of those carbons is the end of a chain. So not possible to have ketones with C2. But when we get to C3, we can. Propanone, butanone, pentanone. So again, -one suffix from the name becomes the suffix in all of these as well. Good. Now there's many more. Pretty much every compound that I introduced in my functional groups video has its own homologous series. You could draw that huge table with 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons for each of them going off into infinity. But I think you get the idea. So here I'll just write the homologous series, the functional group name, and the structure with R groups instead of a full kind of structural formula. So carboxylic acid, CnH2nO2, carboxyl group, R, C double bond O, OH. Ether, CnH2n plus 2O. It's like just 2 alkane chains linked together through 1 oxygen. It's an alkoxy functional group, R, O, R prime, some other R group. Esters, CnH2nO2, ester group, no special name there. R, C double bond O, O-R prime. Then amines with nitrogen, CnH2n plus 3, N. Amino functional group, R-N with 2 NH bonds. That's primary. If the N is bonded to other carbons, that will become secondary or tertiary. I'll talk about that later today too. Amides, CnH2n plus 1, NO. Amido group, R, C double bond O, NH2, or we could even have just an R group there. Things can be attached to that amine, and they often are. Yeah, I'll change one of these H's to an R group. Okay, then nitriles, CnH2n plus 1, CN, cyano functional group. I think I didn't mention that's the functional group name in my previous video, but nitriles are not really part of the IB curriculum. So I don't think you'd be tested on the functional group name of that, but just so you know, it's good to know. R, C triple bond N. And there are several more, I think, but you get the idea. Now, as I said, amine and carbon labeling. We can have primary, secondary, tertiary. It's very good to know which is which and how to identify them or draw them. It provides information on what's attached to the carbon or the amine nitrogen. But the system is different for carbon versus nitrogen. For primary carbons, it means it's a CH3 group at the end of a chain. And not necessarily CH3 group, it can have other things attached, like alcohols or halogens. But if it's a carbon at the end of a chain, then it's primary. If a carbon's in the middle of a chain and it has two other carbons attached, it is secondary. If it's in the middle of a chain and it has an extra branch on it, so 3 carbons attached and one other thing, it is a tertiary carbon. Amines are slightly different though. The definition is how many carbons are attached to your nitrogen. So we have primary amine here. It has one N-R bond, where R is the carbon chain. So one example is methylamine, CH3NH2. There's an N-C bond there, but then there's 2 NH bonds and a lone pair. That's primary amines. Secondary amines will have 2 N-carbon bonds and only 1 NH bond. For example, dimethylamine, CH3NH-CH3. 2 of those carbons are attached to the same nitrogen. And then tertiary amine, this is when the nitrogen is bonded to 3 carbons and there is no NH bonds. So trimethylamine is an example there. So these systems are slightly different, but you definitely need to know both. Okay, some practice. Let's try. This will also just include practice for, naming functional groups and classes that could have been in my previous video. I just decided to push them forward here. So, which functional group is circled in this molecule? Number 1, you might be thinking, oh, that's an aldehyde or ketone maybe, but keep in mind that those are class names or homologous series names. The functional group name is different usually. So this is a carbonyl functional group. Okay, number 2, which functional groups are in this molecule? We have 4 choices, but let's just find them all. So in the top right, C double bond O C. This will be also a carbonyl group. It is a ketone, but that shares a group with aldehydes. COC here, this will be an ether, therefore its functional group name is alkoxy. There is another alkoxy group here, COC. And we do have double bonds, but you got to be careful not to just label them as alkenes because they belong to a bigger group. You always have to look at what the overarching group is. So there are 2 of these, benzene rings, phenyl rings. Phenyl functional group, arene functional group. And then we do have CN groups. These are C triple bond Ns though. They are nitriles, and nitrile name is cyano. But as I mentioned, oftentimes these are not really required for naming in IB. I just told you for fun because they often appear, but they often won't be part of the question, which is why they don't show up in the answers here. So what do we have? Carbonyl, alkoxy, and phenyl only. That is C. There's no carboxyl group. There's no ester group, double bond OO groups, no amino groups. There is N's, but they're trying to trick you. Those belong to nitrile cyano groups that don't even appear in the answers here. And yeah, no esters, so it's not D. Okay, number 3, which functional group are present in the following molecule? Functional groups. So it looks a little more complex, perhaps. Don't be confused by the dark and dashed lines. If you go back and watch my 3D drawings, Lewis structures video, you'll know that those are just representations of 3D molecules, carbons that go into the plane, into the screen, or come out of the screen. But they don't really require us to consider much for just finding functional groups. So we have here OH attached to secondary carbon. So that's alcohol secondary. Oops, made the mistake of writing the class name. As I said, you got to label that as the functional group name, hydroxyl. What else? We've got alkene here. It's just a carbon-carbon double bond. We've got NC-NC-NH here. This is amine secondary type. Okay, so this is an amine or amino group. And amino, this is a secondary amino group. You can often write the secondary with a 2 or 1 or 2 or 3. This is 2 for secondary. Circle in the top right, that means secondary. And I'll also label our hydroxyl down here also as secondary. 2 carbons attached to that alcohol carbon. And what else do we have? We've got this group, a CO double bond, but it's also immediately connected to a COC group. So altogether, that is an ester group. Okay, so hydroxyl secondary, alkene, ester, and amino secondary as well. That's pretty much all there is here. All right. Next, number 4. Which functional groups are present in the following molecule? So lots of things going on. Start in the bottom left. C double bond O, also connected to COH. So that is a carboxyl group. You know, don't say that there's a ketone or carbonyl group inside there, because it expands to a carboxyl group with that OH group. That's the real name. All right, then here, hydroxyl group. And that is, again, secondary. We've got quite a few alkenes. We've got one carbonyl here, ketone. And we've got COC here, alkoxy. And I think that's it. Alkenes, these 3 here. All right, carboxyl, hydroxyl secondary, carbonyl alkenes, alkoxy. All right, moving on. So the next section, 3.2.4, is just about physical trends in homologous series. Mainly, there's one physical trend we're looking at, which is boiling point and possibly melting point. So here, let's look at just the alkanes, the simplest series: methane, ethane, propane, butane, pentane, hexane, CH4, and then we're adding one carbon each time to the chain. The boiling point starts at minus 161, very low, melting point minus 183. But as we add more carbons to our chains, boiling point goes up, minus 89, minus 42, minus 0.5, plus 36, plus 69. Okay, same trend does also appear for melting points, although it remains lower as expected. But why does this happen? Again, it's all to do with intermolecular forces. These are covalently bonded molecules, so they're attracted to each other, and phase changes will be determined by intermolecular forces. These only have London forces. London forces are determined by number of electrons, volume of the electron cloud, polarizability. All of those things increase as we add more carbons to the chain, increase the size of this molecule. Therefore, boiling and melting points go up, and it's fairly kind of linear, even spaced after the first few. There are some big jumps there at the beginning. So to expand on this, I want to remind you guys about distillation. So fractional distillation is an important technique to be able to separate members of a homologous series. Members of a homologous series increase in boiling point as the number of carbons in the chain. We can call that number n as that increases. This is due to increased opportunity for instantaneous dipoles and London forces, and just more electrons and bigger size in general as well. Therefore, organic compounds can often be separated by how they boil at different temperatures. Remember, all molecules and atoms experience London forces. Even if you might label the strongest force as hydrogen bonding in a carboxylic acid or something, if you look at the homologous series as you add more and more carbons, you're still increasing London forces, and that's still going to increase boiling and melting points as you go through the series. Okay, reminder of distillation. We put liquids in a flask, heat it up. It's a mixture, and then the lower boiling point, the more volatile things, will evaporate and boil first. We catch them in a separate container. Then once the temperature starts changing again and goes to the next compound, we change our flask and we collect the next thing. This could be used to separate members of a homologous series because we just saw they have different boiling points. But still not that easy. Here's a good graph of number of carbons in a chain. So it's kind of like going through a homologous series from left to right. It goes from smaller members to larger members on the right, and then boiling point in degrees Celsius on the y-axis. You can see the alkanes and alkenes have some big jumps at the start, but they will kind of even out and get a constant slope at around 7 or 8 carbons, and then it's just kind of linear, like increasing the number of carbons increases the boiling point by some amount. Then alcohols and carboxylic acids, these have dipoles and hydrogen bonding, so they're going to start much higher up in boiling point. You would have to overcome the hydrogen bonds to separate them. But they also have kind of a linear slope even from the start, where increasing the number of carbons increases the boiling point by some set amount. And I do want to mention it's not just boiling point that changes here. It's also like solubility, polarity, and hydrophobicity. As you add more carbons to a chain, and that's the only thing you do, you're decreasing the polarity kind of, and you're increasing the hydrophobicity. That's why I mentioned in my covalent physical properties video, if you look at the organic alcohols,
ethanol, propanol, butanol, and when you get to around pentanol,
is when they start becoming insoluble or not very soluble in water. Even though they have OHs and hydrogen bonding, the long carbon chain becomes very hydrophobic and pulls the molecules together with themselves instead, or stops them from being able to be surrounded as well by water and not mixing into homogeneous solutions anymore. Anyway, sidetrack. Moving on. Fractional distillation. This is a really important idea. So, as I said, distillation can be used to separate members of a homologous series, but you can't just do it once. Many of these are very difficult to separate by distillation. They form what are called azeotropes, where you can boil one of these off and you'll get a certain percentage change or new percent in the new mixture. For example, if we start with toluene and benzene, I'll just draw the structures of those so you know what we're dealing with here. Benzene, hexagon with alternating single double bonds. Toluene is the same, just it has one extra methyl group attached, CH3. So these are very similar. They belong to the same homologous series, but they can be separated with distillation. But if you do this once, if you have a 50-50 mixture to start, you're going to have an 80-20 mixture next. That's often not pure enough for most people's needs. So you do it again, you get 97% benzene, benzene being the more volatile one, lower boiling point. But even that's not pure enough for some people. You might end up doing this again and again and again if you want to get 99.99. And it's very energy intensive and labor intensive to do this. And this is not even one of the worst azeotropes, I think. A lot of these, you might go 50, 60, 70, like much slower, up to pure amounts. And some of them I think you can't even get beyond certain percentages. So what's happening here is that every time this distillation fully evaporates and condenses the mixture, it gets a little bit closer to being pure. But what we want is as many cycles to happen as possible of boiling and condensing. So in the industry, you might have big distillation chambers like this, fractional distillation, where we have crude oil just put in at the bottom. We have very high heat, so all volatile organics will be boiled and evaporated off. Only some very heavy, sludgy, kind of polymerized junk will remain at the bottom here. It just can't boil even at these high temperatures of 350. So those will get pulled off, as they're not totally useless. They can be lubricating oils or bitumens, like to make asphalt and roads and things. But as we start going up, temperature will decrease, and we'll have these different chambers where we collect different types of fuel. So fuel oil for large ships and tankers, heavy oils would be first around 300 to 250. Diesel oils at 200, kerosenes at 150, jet fuel, gasoline at under 100, and then gases like not gasoline but actual gas phase, hydrocarbon gases, natural gas kind of thing, refinery gas, LPG, propane, ethane, those kind of things will be at the very top. They have the lowest boiling points. And so this is what we try to do. We try to get these different sections that can separate different groups. In crude oil, you might have dozens or hundreds of different compounds mixed just when you pull it out of the ground. It's just a black kind of slimy mess, right? But this is what we do to get useful things out of it, pure things. Now, building this giant kind of contraption in the lab in every lab, like every university or high school lab, is not very practical, but we can use condensers that have a lot of places, a lot of surface area for condensing and boiling and recondensing to happen again and again. And a very similar thing can happen where we have a gradient of temperatures. And, you'll see these tubes that have a lot of coils inside or little bubbles like plastic beads or shelves. Something that allows surface area for condensation and boiling to happen many, many times. And hopefully we get the purest things coming out into our collecting flask that way. All right. Then that is the end of what I have to say today about homologous series and maybe how to separate them, name them a little bit, identify them. Hopefully you learned something. Next video will be more about naming. I hope to see you there. See you next time.